We have the pleasure of having Dr. Vinodh Bandaru with us to speak on magnetofluid equilibrium and stability in fusion plasmas. So Vinodh did his bachelor's at Pondicherry University and is a Master of Technology MTech from IIT Kharagpur in thermal science. And then he has worked in GE Bangalore for about 4.5 years. And then he did his PhD with Professor Schumacher in mechanical engineering in TU now. And then at the moment after that he continued as a postdoc at TU now. And at the moment, he's a postdoc at Max Planck Institute for Plasma Physics in Garching. And his interests are in the area of MHD, turbulence, computational methods in fluid mechanics, and large-scale instabilities in tokamak plasmas. So with that, the digital floor is yours, Vinodh.
So thanks a lot, Abhishek. So I will today give a brief overview of a part of my work in the field of disruptions and relativistic electrons in plasmas for fusion energy generation. So I know this is mainly a turbulence seminar. So I have worked fairly very little in turbulence, and I'm mainly in numerics and I work on fluid dynamics too, but not. I haven't had time to really delve into too much of turbulence theory. So this would be mainly focused on fusion MHD. So first, a bit of background on where we come from. So we all know that nuclear fusion is a sustainable alternative for baseload energy. That is the main idea of fusion is that hydrogen has two heavy isotopes called heavy hydrogen. These are called as deuterium and tritium. So what I show here is the nucleus that has one proton and two neutrons. That's called tritium. Deuterium means it has just one neutron. So if these two are somehow fused together, then the output products are going to be helium and a neutron. And now the total mass of these output products is less than the input incoming products by a small amount, and that loss of mass manifests as kinetic energy of these outgoing particles. So since neutron is 1/4 the mass of the helium, so it gets 80% of the energy, and the aim is to obtain energy from aim is to obtain energy from this neutron. That is, we use this neutron to slow it down onto something called as a blanket, and so that kinetic energy of this neutron gets converted into heat, and this heat can be used to produce steam and run a steam turbine. So now, where do we get this fuel from? The deuterium tritium. So the deuterium is a heavy hydrogen and is abundantly found in seawater, and there are enormous amount of resources even on the Earth's crust. So also tritium has a half-life of around 12 years, so it is not naturally found. So that means that anything that would have been on Earth would have been lost by now. So that due to that, tritium has to be prepared on the site. So here tritium is made in a way by what is called as breeding. So this means that once the neutron is slowed down, it is made to hit onto a lithium ion, and this gives us tritium. So in a way, one can have a self-sustaining fuel cycle, and we need lithium for that, and we have enormous amount of lithium too on the top layer of the Earth and in oceans. Now, what is the outcome of output of this? This basically, like I said, the ash here, if we look at this as a fire, the ash is the helium that we have, which is harmless, and the energy is coming from neutrons, which we take out as heat. So basically, we would have enormous amount of energy, because nuclear reactions have about a million times more energy per unit mass, and so that's why we would have an energy from 1 kg of this fuel that is equivalent to 12 tons of coal or so, and there are no carbon emissions, and there are no problems. Unlike nuclear fission, there is no harmful radiation, long-term radiation, or there is no problem also of any nuclear accident or possibility of making weapons out of this. Now, in order to get energies of the order of what we need in a nuclear power plant, we must ensure that there are enormous number of reactions that happen at any given time. So this means that to have lots of such reactions, it's only possible to have possible at very high temperatures. That means you have very large amount of collisions happening that gives us energy. And at these temperatures, the fuel will not be in the form of a gas, but rather fully ionized. So unlike a gas where we have molecules, in this case, we would have a plasma where the nuclei or the ions are separated from the electrons, and you have a sea of charged particles. So this is not a strict definition of plasma, but loosely speaking, for the time being, we assume that this is the plasma. Now, how do we hold this whole thing? Because the temperature is about 150 million Kelvin. How are we going to hold this? Because any concrete or steel or metal container will be evaporating instantly. And what is done to do this is that we apply a very strong magnetic field to ensure confinement. The main point is that if we leave a charged particle in a magnetic field, then the main motion of the charged particle is that it gyrates helically along the magnetic field. Because of this, it doesn't really stray away from the field, and this is what used to actually used as a cage to contain the plasma. So in short, we have, let's say, the plasma in the form of a toroidal shape here, like a donut. Maybe I've seen in earlier presentations too, where a strong magnetic field is applied and the plasma is fully confined. But it can be shown that just applying a magnetic field in the toroidal direction is not sufficient, but what is necessary is what is called as helicity in the field. Because if we don't apply, this whole thing will keep expanding in major radius, and this cannot be allowed to happen. And there are many ways of applying helicity to the magnetic field, and one way is by applying a plasma current. So the green lines that you see is the plasma current that goes around the torus of the plasma. And this plasma current, if you look at this plasma current, this produces a circular magnetic field, but what we have already applied is a toroidal magnetic field. So the net effect of both is a helical magnetic field. So in essence, if you take the torus here, this is the cross section. Usually the cross section isn't circular, it's much different, but effectively you will have lines of B field going helically along the toroidal surfaces, and also current density lines that that has an angle to the magnetic field surfaces. So largely they are toroidal, but they have an angle that ensures equilibrium. So in a simplistic way, one can see that the equilibrium is maintained by the simple. I mean, if you take the Navier-Stokes equations and remove all the minor terms, you have the crossing of J and B, which leads to a minor radial force that balances exactly the pressure, minor radial pressure gradient in the plasma. This is the most simplistic picture of seeing it. So in terms of the overall picture, like I said, we have a plasma fire in which there are nuclear reactions. There are neutrons coming out from the plasma with large kinetic energy. It's being slowed down in a blanket. We have a lot of heat, and the heat is used to boil water and make steam. And we use the Rankine steam turbine or so to turn a generator that gives power. There are lots of auxiliary systems, diagnostics, and so on that goes into it, but we do not worry about this in this talk. We would only be worried about the actual plasma itself in the tokamak. Now, the plasma in the tokamak has lots of phenomena that are going on simultaneously. So it's a rather complex system, and typically different models are used to look at different aspects of the plasma. So here I show that there are a lot of time scales and length scales involved. You see that they go over several orders of magnitude. So close to about 10 orders of magnitude in time, for example. So my focus of work has been in the area of MHD or magnetohydrodynamics, and this This is some kind of an approximation, so to say, when it comes to plasmas. So if you look at incompressible fluid flows, then if you say MHD or hydrodynamic equations in a DNS, that's sort of a complete theory or self-sufficient theory. But in the case of MHD, this is a sort of an approximation, because plasma particles, strictly speaking, have to be treated kinetically or by the use of what is called as the F formulations, that is the distribution functions. But when we say MHD, we assume that the distribution is Maxwellian, and then derive some sort of reduced formulation which gives fluid equations. So in that sense, fluid equations aren't perfect, but for a lot of for a lot of phenomena that we look into, they're extremely good and work very well, actually. So in terms of the plasmas in the tokamak, apart from being multi-scale, there is also a strong nonlinearity involved, and there are extremely high levels of anisotropy involved in fusion plasmas. For example, the thermal conductivity of the plasmas is about 10 to 9 orders of magnitude larger along the field lines rather than perpendicular to the field lines. So these make numerics also quite difficult in these situations. Now, over the last 60 years or so, there have been enormous amount of number of experiments that have been made, tokamaks that have been constructed and experiments made to study fusion, and there has been a lot of progress, but until now, at power plant scale, there has not been any demonstration of energy production. But in the recent years, the fusion has reached some kind of a tipping point, so to say, or an inflection point, where there are several different newer experiments coming that are becoming more power plant relevant. One such example is called as an ITER, which is an international collaboration of a fusion experiment that's being built in the south of France, and the aim of which is to produce 500 megawatt of output thermal power from an input of 50 megawatt. And it is seen largely that if ITER happens successfully, then it paves the way for fusion power plants. Now, this all looks rosy, but in reality, fusion has a number of problems that has to be solved before it can be successfully replicated in a power plant conditions. So these problems range from purely physics problems to engineering or technology issues. But I would just focus on one specific thing, which is by far the most burning and urgent thing to be solved. This is known as disruptions in relativistic electrons. So now we have seen disruption means basically that there is a sudden drop of plasma temperature due to large-scale instabilities. That is, we have seen that we have a nice hot plasma at 150 million Kelvin, producing fusion reactions and neutrons and energy and so on. But there are sometimes, rarely but not often, that there are instabilities that leads to a complete stochastization of the plasma, that the temperature drops very fast. So, for example, this is from a particular experiment in the UK, where you see the temperature with time, which suddenly drops by about a factor of 100 within a millisecond. This can be seen in a much better way from this small video that you're peeping into a tokamak plasma, where you see that suddenly the whole thing is quenched. So it is not that the plasma is not gone, it's just that the plasma cools down. So the pink is the plasma, you're looking from a window, and you see that suddenly the whole of the fire is sort of quenched instantly. So this leads to enormous amount of thermal and magnetic energies. For example, ITER has about so much of both thermal and magnetic energies, and these would be dumped in a few milliseconds. So this is damaging to the machine in so many ways, because when we say large thermal energy, all this has to go through a very thin region, which also we have seen in a previous talk where we see that the heat fluxes are going to be enormous, Likewise, a sudden loss of magnetic energy in this form, the colloidal magnetic energy, can lead to very large currents on the containing vessels, and they lead to very large amount of forces. And one side effect of this also is called as relativistic electrons.
Vinodh, can you just go back? I want to understand, just to go back a little. So here, what energy is going into what? I mean, we have large scale magnetic energy, which is when you cool down, what happens? I mean, I don't fully understand. When it cools down, the magnetic field, what happens? Could you kind of just
yes,
just enlighten me a bit?
Yeah, no problem, no problem. Good that you asked. So when the plasma cools in such a short amount of time, what happens is the way the cooling happens is that effectively there is a loss of heat in the minor radial direction. If you look at the cross section of the plasma, and this heat goes into a small, has to go out parallelly via the magnetic field lines, and it goes to a small part called diverter. So this metallic part called diverter, which is made out of tungsten, so within a small strip of about a centimeter or so, all this heat has to get dumped. So the material limits are such that it is going way beyond the limits of so this cannot be tolerated, and that's what is called as large thermal loads being dumped. And once the plasma is cooled, the plasma resistivity increases by a factor of 1,000 or so, because fusion plasma has a resistivity that there has a conductivity that increases as T power 1/2. So this means that when the temperature drops by a factor of 100, the resistivity increases by a factor of 1,000, and this means that the plasma current has to decay fast at the resistive diffusion time scale. And when the plasma current decays, this means that the colloidal magnetic energy is also decaying, and this happening so fast is going to create sort of an induction effect on the conducting structures surrounding the plasma, and these currents in the surrounding structures are going to cause forces on them down there. This is what is what I said loosely as magnetic energy is being dumped. So in short, it's a strong change in the electromagnetic structure that is causing the large mechanical loads on the surrounding structures. Is that clear, Professor?
Please go ahead. Please go ahead.
Yeah. So one more effect of this disruption is called as relativistic electrons. So these are electrons that travel close to the speed of light with energies of the order of tens of mega electron volts. Now, why are these formed? So when the plasma cools down, as I said, it's the resistivity increases. This means that from the Ohm's law, we can see that we have a large electric field compared to what it was when the plasma was hot. And this electric field can actually accelerate charged particles. So the ions are much heavier, are accelerated more effectively. And there is one very interesting property in plasmas, that the collision frequencies drop as the inverse cube of the velocity. So that means that as the electrons are getting accelerated, they are going to get less and less collisions from the surrounding plasma, which means that the drag force is decreasing as it gets accelerated. This means that as we go on, as the electric field goes on accelerating the electrons, they literally tend to get accelerated indefinitely until it reaches relativistic velocities where it can go beyond the speed of light. So these electrons form a beam, so to say, which means that initially, let's say we had 15 megaamp of plasma current, but after the disruption, almost all of the current is going to get converted into a relativistic electron beam, say about 10 megaamps or so, because the current would decay before these runaways are formed. So the main implications of this is that if we lose this relativistic electron beam in an uncontrolled way, then it can actually, because of its large energy, it can actually damage the walls. So already in the existing machines, we see severe damage of surrounding structures, and in machines like ITER, this is not tolerable because in the environment would be nuclear, and one person cannot really go and replace this, and also replacing would take an enormous amount of time that such downtimes are not allowed in power plant situations. So that means that this has to be really solved, and to solve this issue, one has to understand the physics or dynamics of how it is formed and how it interacts with instabilities in the plasma. So basically, I'm now done with the intro part on what the work is about, and now we get to some details. So any questions until now? Looks like not the case, so I then proceed further. So I would give a brief overview of how equilibrium changes in a tokamak plasma when we have relativistic electrons. This I show by one kind of reduced fluid model for relativistic electrons. So in this case, the total current density J is assumed to have two components, one by the background plasma where we have the ion velocity and electron velocity. N is the number density of the charged particles and E is the electron charge, and there is an extra relativistic component of the current that gets added to it. So sum of both is going to be the total current density, and the relativistic current density itself can be easily defined as with the velocity of the relativistic electrons. Now, and there is what is referred to as a drift kinetic equation, which is what I said is an equation that governs the distribution function for particles in a plasma. And if it is integrated over the velocity phase space, one can easily obtain something of this kind. That is, the runaway density has a typical advection with various velocity components, but it has also sources of relativistic electrons, which are the primary sources, which are what are accelerated by the electric field, and there is a secondary source, which are formed when a relativistic particle hits another particle. So when particles are relativistic, they have much larger energy than what is apparent from their velocities. So if a relativistic particle hits a normal particle, the other one also becomes instantly relativistic. That is, the first one loses its momentum but not its velocity, but the second one gets a relativistic velocity. So the velocity itself comprises of a parallel velocity along the magnetic field and what is called as an E cross B drift and a curvature drift. So I would get into details of this very shortly. So now, to obtain the equilibrium on how the plasma is in equilibrium in a tokamak plasma, we now go through a short exercise. So for this, one needs to first compute what is the total current density contribution from these relativistic electrons. So for that, I start with the velocity. So the velocity due to the guiding center drifts, that is, when we have a particle that is gyrating along the magnetic field, that's a full motion. But if we take the center of it, that we call it as a guiding center. So we only look at guiding center, which means we are averaging around the gyro orbit. So the guiding center drifts of a charged particle can be represented as an E cross B drift. That means when you have an electric field and a magnetic field in a plasma, then you have an effective motion of the particle, not just helically along the magnetic field, but also along E cross B. And that is what is referred to as a grad B drift. That is, if you have changes in the magnetic field magnitude, then you have a motion in this direction. And there is also what is called as a curvature drift, where if the magnetic field is curved, then you have a drifting of particles along the curvature cross the B field. So the gamma is the relativistic factor here. V is the velocity of the electrons. And the V perp and V parallel are the perpendicular and parallel components of velocity. So the curvature itself is defined in this way, where V is the unit vector along the magnetic field. And now as a simple approximation, if we just take the current density due to the guiding sector velocities itself, then it would be just the E times nr times this velocity. So that would lead to a current density due to the guiding center drifts in this form. So basically, you see same terms here, but I've just clubbed these terms into what are called as P perp and P parallel, but there's nothing different that you see here. Now, this is not the only component of current density that we have, but there is a current density contribution to what is called as magnetization current. That is, if you take a plane area and take a charged particle that gyrates along the field line, so you see that a particle can pierce into the area and also out of the area. This means that when you are within an area, the effective current density perpendicular to the area is 0, but when you are at the edge of the area, you see that the particle pierces once, but it goes outside. So this means that there is a net current when you take a finite area due to this effect of edge effect. So if one can actually compute the current density contribution due to this magnetization currents, and that comes out to be something of this sort. And the current, this is the total current contribution, but the current density itself, I mean, I is the area integral of this, so J can be very clearly seen to be the curl of this term. So this can be actually expanded into these three different terms here. So basically, this is just algebra and nothing more from here to here. So now previously we have seen that current density component due to the guiding center motion, and now we see the current density due to the magnetization effect, and the sum of both would be the net current density. So we can see that previously we had some term similar to this, but with an opposite sign that gets cancelled. But this would not get cancelled because it had a P parallel here. So effectively, if we do the net current density, the sum of both components, then we have an E cross P part and the curvature part and this grad P per part. So doing a cross product of this equation with the B field gives this. So you have a JR cross B here. And the E per component and the P per component in this one. One can do an ordering and see that mainly the balance is between this term and the P parallel kappa. So now the main point of all this, if you forget about details of these equations, the main point is that in an ordinary plasma equilibrium without relativistic electrons, all the drifts none of the drifts actually contribute to the equilibrium. In fact, it's only the magnetization current that contributes to the current density that can cross with B field. But in the presence of a relativistic electron current, the curvature drift component does not cancel off because the P parallel is far larger than P perp, because this is relativistic momentum actually, and because of that, the nature of equilibrium changes significantly. So, like I said, the major component is going to be mainly this term and this term, which determines the equilibrium. Likewise, one can also look at the perpendicular momentum for the background plasma. This would look similar to the Navier-Stokes equations, but we are writing it for the background plasma species as if it's a separate velocity, and there you see that only the thermal component of the current crosses with B here, and P is the thermal pressure. Now adding both of them will give us an equation for the whole plasma itself in this form. So in terms of if one wants to solve the whole problem of interaction of these relativistic electrons with the background plasma, so one has to then solve all the governing equations. So we can write also a parallel momentum for the relativistic electrons that also includes various kinds of radiation sources. So electrons in the plasma can be subjected to collisional drag, and also two kinds of radiation called Bremsstrahlung and synchrotron radiation. So I wouldn't get into details of this, but we can just see that they can lose energy via radiation. Likewise, for the background plasma, one can write equations, governing equations for the electron density, the thermal energy, and our usual Maxwell's equations, and also at colder temperatures we can form neutrals, and there are instances where impurities are injected into the plasma, so we also have equations for impurity and neutral species. So all of these are typically used in codes, the MHD codes, to understand what's going on in the plasma. Now, I would quickly take you through how the equilibrium would be different with these relativistic electrons. So, if one can, for an axisymmetric equilibrium, which means that there are no variations in the toroidal direction, one can write the magnetic field in this form, which is clearly divergence free, and the current density, the toroidal component, toroidal is going along the donut or the torus, and the colloidal would be of this form. And the velocity of the fluid velocity of the runaway relativistic electrons can be written again in this form, for which this would be divergence free, because we don't consider any sources for these. So from the background plasma momentum, like I said, only the thermal part of the current density is taken into account. Doing a simple vector operation would, after some algebra, gives a result of this sort, which means that the thermal current still lies on the flux surfaces. This is a function of psi, which is a colloidal flux here, whereas the relativistic part of the current density would not lie on the flux surface. So here U is like a stream function for the runaway electron colloidal current. Likewise, from the relativistic electron force balance, we can do a cross product with grad U, and after some algebra get relations of this kind, which brings in what is called as a generalized angular momentum that has the flux here as well as the angular momentum of the relativistic electrons. R here is the major radius in this case. So what we can see is that the shift between the surfaces of the flux and the relativistic electrons increases with the energy of runaway electrons. Likewise, we can take additional projections. I wouldn't get into details, just maybe skip these, but to summarize, we can arrive at a modified form of Grad-Shafranov equations, which of course are different from the classical tokamak equilibrium, that can actually describe equilibrium in the presence of relativistic electrons. Now, in terms of physically, what really changes is that, like I said, with relativistic electrons, the motion or the orbits, net orbits of these electrons are different from the flux surfaces. So you can see that the A represents the orbits of these electrons, and psi represents the flux surfaces. I'm just looking at a cross section and plotting these surfaces, and you see that there's pictorially it looks less, but actually there is a significant shift in these surfaces, and this shift can actually cause significant differences to the stability properties of the plasma. In fact, it can be also analytically derived on what would be the kind of shifts that we can obtain at various energies of relativistic electrons and at various kind of current profiles within the plasma, and we can see that up to several centimeters of shift can happen, and which is much larger than what is called as a mode width in fusion plasmas. That is, typical instabilities happen at much smaller length scale than what we see here, and hence the stability is going to get affected significantly. Now, I would very quickly show one short example of what kind of instabilities are looked into and how it is being studied. So in our group, we use what is called as Jurek, which is a massively parallel fusion MHD code. It's 3D, but with 2D flux surface aligned finite elements and a Fourier in the toroidal direction. It's isoparametric, and it takes into account the exterior fields, that is the vacuum and also all the coil fields, by non-local integral magnetic conditions. The solver is basically here mainly we use the GMRS with preconditioning. So the equations, for example, what I have shown until now, these are all implemented into this code, and this is used to study different experiments, and also cases which are not experiments but which we want to look at. So one example that I show here is that of an experiment at Tokamak called JET in the UK. This was a very important result that has been obtained recently. That is, in the experiments, there was a disruption. You see that the plasma current drops, and all this current is relativistic current here. So this is time that you see in seconds, and this is the plasma current. So there is a beam of relativistic electrons in the plasma, and at some point, a beam of deuterium is injected into the plasma. This is done by using pellets or frozen pellets of deuterium, and post that it is seen that the plasma current rises slowly, but afterwards there is a strong instability that leads to a crash, and it was seen that at the end of the experiment there are in fact surprisingly no damage to the wall. So it was necessary that we understand what's really going on, such that we can replicate such a phenomenon in ITER and try to find a solution for the problem. So this was the aim, and for this I start with the plasma state just before the strong crash and see what's really going on. So like I said, I start with an initial state where I start with a hollow profile for the relativistic electron density. So the fact that this is a hollow profile could be obtained from various indirect clues from experimental data. I wouldn't get into that, but the fact that it is a hollow profile was rather important for the kind of instabilities that we see here. So starting with such a state, I introduce small perturbations in the plasma and see how things evolve. So here with time, I show colloidal magnetic energy perturbations of different modes. We see clearly that the n=1 mode is the most dominant and unstable. This grows, and over a time there is a nonlinear activity and other modes to grow, and this leads to eventually nonlinear interaction of the modes and stochastization of the plasma. Now, how it really looks like in a different way to see is via what is called as Poincare plots. Here, what I show is a cut cross section of the plasma. So this is the wall, and this is the cut cross section of the plasma. And the surfaces that you see here are formed as a result of taking one specific point and just keeping on following the field lines toroidally again and again, and just plot the locus of where all it pierces the plane. So that's called as a Poincare plot. So if you see a line that is continuous here, that means that the flux surfaces are closed. But if you see anything chaotic here, that means that the field has become stochastic. So we start at this stage before the nonlinear activity. So we see that there are two chain of islands or magnetic modes that have started. This is called as a double tearing mode, so to say. So this is, let's say, the source of instabilities at both these locations. And we see that the outer region, it first stochastizes here, and slowly the stochastization is proceeding inward, so that the closed flux surface region is shrinking. And at the same time, I'm also plotting the color, which is the relativistic electron density. You see that when the plasma is stochastic, there is effectively a net diffusion of particles in the minor radial direction. That's why you see that they are much lesser density, because they are getting lost quickly, while within the closed regions they are not getting lost. So eventually the plasma shrinks, the flux surfaces shrink, and more or less more than 90% of these electrons are lost, and they are lost in a very distributed way. Eventually the flux surface is reformed, but there are no relativistic electrons left in the plasma. So this whole qualitative, yeah.
So I am sure you guys are aware of this Hamiltonian chaos. This Cam Turai, these are all torus. K. Kolmogorov, Arnold, Moser, Cam torus breaking. Is it done for this or no? Hello?
No, I'm not aware of what you mentioned.
No,
So
in general, for tokamaks, it is done.
Hello?
Pardon?
Yeah, I'm saying in general for tokamaks, it is done. So we know where the camp tori exists.
So
but
these
not
are the
for
camp
the,
tori,
not for the, yeah, but not for the runaways, because runaways are something that do not, that like violates the fundamental thing. So the, like, within the closed surfaces, all those camp tories, we know where the camp tories.
Let's discuss it. I think they, to me, they look like camp tori breaking one after the other. But let's discuss it then.
Exactly, yeah.
Continue.
Sure.
Yeah, I'm close to finishing. So this phenomenology or qualitative behavior is in fact seen to be in excellent agreement with what's in the experiments. So we largely understand, let's say, the overall scheme of what's going on. And in terms of why there wasn't any damage, we can look at flux and fluence on the wall. Fluence is an integral of the flux in this case. And we can see that in time we see that it's a short burst of relativistic electrons on the wall, similar to what it is in the experiments, and the extent, the psi n is a normalized flux function, which in a way represent the distance from what is called as a limiter point. So this happens over a larger distance here, which sort of explains why we do not really have a damage, because it's quite distributed, because instabilities start on the outer region. And in terms of the fluence too, we see an n equals 1 mode in terms of the fluence along the toroidal direction to from the main instability that we have. So that's it largely, and yeah, I think with this I could. I think I have given a rough flavor of what kind of things that we look into in our group, especially in the topic of relativistic electrons. And yeah, if you have any questions, I would be glad to take.
Okay, thanks, Vinodh. So, Abhishek, you want to monitor this? I mean,
yeah. So,
okay,
so if
please.
there are any questions, then please raise your hand, and or you can just unmute yourself and ask a question.
Okay, so I think
Fine,
yeah, please. So let me ask this. So we can go back to that slide.
Yeah.
Yes, here. So what is told in okay, CAM is a okay. I mean, this is a slightly complicated, not so trivial, but so okay. So the points where there's these two of those contours, you can call it contours. No, they overlap. They're touching, right? The red region, and that's a saddle. Okay. And
you mean here?
Yes, precisely. The four of them.
Mm-hmm.
And that's where the instability grows.
Mm-hmm.
Okay. And it happens to most unstable torus first, then and finally everything breaks. The last one is Kolmogorov tori or whatever. So there's a standard literature for this. And to me, it looks like it is going in that way. So finally we get, figure E, the last, well, one before last. Okay, that's where almost everything is broken except some tiny ones are still left in the center.
Yeah.
So there are tori of different levels of stability. Well, they're called irrational number and the winding number. So the standard book, I mean, I can also refer to you some books. You can look at it by Hilborn. Stuttgart does not cover this, but Hilborn covers this stuff reasonably well. Or if you want to go to more, so Hamiltonian chaos, you just look at Hamiltonian chaos and you'll find this. And I think Rupak knows about it for some other systems, but I mean, to me, it looks like there's some connection. Okay, it may not be one-to-one.
Yeah.
Yes.
This is.
Yeah,
very
I must say that this looks like turbulence, but in a way it is not turbulence. It's just
don't connect with turbulence. CAM is different than turbulence. Huh?
Yeah.
degrees of freedom are here. You don't need too many. We have few more.
Yes.
Camp tori is what you should look at it. I mean, this sequence is very okay. Rupak, you are saying something. Don't look at turbulence. This is chaos. Okay.
Yes.
And the Russian group, Sagdiv, rolled Sagdiv, what is his name? Zakharov. They have done a lot of work on this. Sagdiv, if you look at it, you would have.
Yeah.
Okay, Rupak, please go ahead.
Right. So, Vinodh, just for clarification.
Yeah.
So what I think sir is talking about is chaos in magnetic fields. So it's like the magnetic fields are chaotic, not the plasma. So forget about the plasma. If there is only the vacuum magnetic field, that itself is chaotic. So Hamiltonian chaos that he is talking about is the chaos of the magnetic field lines itself, whether they are closed, whether there is some overlap region or not. I think in PPPL,
I got it.
In PPPL, specifically for tokamaks as well as for stellarators, there are a lot of works done. You can look at the book written by Roscoe White, probably you know. Roscoe White. So he's retired, but anyway. And recently you can look at works by, so these are all theory. In PPPL theory group, you can look at the works by Stuart Hudson. He was the previous acting head of our department. And if you want to look at the simulation perspective, you can look at works by Vinicius. He is our colleague here. Vinicius Duarte. He's now a staff here. He worked with Roscoe. And if you want to look at some experimental perspective, like how these are affecting how experimentalists can control these, I think you can look at the works by Walter Guttenfelder. He's also in Princeton. He works in NSTX. So he has shown, like, in theoretically, you propose a camp theory, like you can actually identify where the camp theory exists, and then can you control your plasma transport via those things in experiment. So yeah, I think these are they have worked since several years. Roscoe has worked on this since last probably 30-40 years or more than that, if not.
But the standard book by Hilborn, that should give him some idea.
Yeah, that's perfect for from non-plasma perspective. These are all like exactly, these are from plasma perspective, like tokamak, I should not call it plasma perspective, I should say from tokamak perspective. So if you have different tokamaks of different radii or like different parameters, where will be the camp surfaces explicitly for the tokamaks. You can actually look the works by Stuart. He has done several years of work for stellarators as well as for tokamaks. So yeah.
Anyway, so we can give other people some.
Yeah, sure.
Thanks for the additional references. I will have a look at them. Yeah.
Okay.
Yeah. Are there any questions or comments?
Okay, maybe I'll ask another question. So
yeah.
So if you go to when you started the definition of V advection, can you go back to that slide, the V advection? Yeah, no, V advection was here. So we have lots of velocities, no? When V advection, the VI, V. So right now, what you're talking about, the magnetic field, which was those torides or the closed loops, they are coming out of V advection, or what are they coming out of?
Okay, the magnetic field comes because of two components. One is that externally a toroidal field is applied by coils. So I quickly go there.
I got that. That I understand, but
yes, these blue color coils cause a magnetic field of this in toroidal direction. But apart from that, the current density which is driven in the plasma, that creates a colloidal component of the magnetic field. So the net effect is a helical field, which is the B that we are talking about.
But then there is a turbulence. So what is causing those fluctuations and those merging and so on, or the chaos actually? Let's just say So the slide which we are discussing with CAM, what is causing those fluctuations? Is it the V advection or V fluctuations, or which among them?
The current density gradients is what causes these things. So when the current density gradients is strong near the what is called as rational surfaces, that is among these surfaces, surfaces that have the what is called as the safety factor. That is, if you go along the field line, there are surfaces where you exactly come back to the same location. So these are called rational surfaces.
M by N ratio, P by Q ratio. I think this is familiar with the KM Tori formula.
Yeah, that is a rational number.
I think the jargon that we use is probably different. So these are the surfaces that are most conducive to for instabilities to grow, because there is no mixing as we go along the field lines. So that's why you see specifically on those surfaces that it is growing, but the primary driving factor is gradient, a strong gradient in the current density.
So if I can add a little bit, when Vinodh said safety factor in plasma physics community, we call it safety factor or beta, and probably and the beta is basically M by N ratio or P by Q ratio, which Mahendra sir, you are talking about the CAM Tori. So usually we keep it below 3 or something. The beta is exactly the P by Q ratio or M by N ratio, whatever. So it's like how many turns you have covered in one direction. So another thing probably Vinodh will tell, beta is like magnetic pressure by kinetic pressure or things like that.
I think beta is different here. I think this is Q, what I'm talking about.
Sorry, Q, right?
Yeah.
Beta, you were talking about the kinetic pressure by magnetic pressure.
I see. All right. So I guess we don't want to bore the audience. Maybe we can close the meeting, then we can just continue some more discussion.
Sorry, yes.